Gaussian elimination with BEFT technique. Sometimes we ask you to use Gaussian with BEFT, and sometimes we use Naive elimination directly. So Gaussian-Jordan method, it helps us to have only forward elimination and no need, for example, for back substitution. It has the same problems like Naive Gaussian elimination, and also it can be modified to partial BEFT elimination. Uh, Disadvantage, this you can see disadvantage here. It takes 50. Yeah, no, this is disadvantage here. It takes 50% more time than Naive elimination. Okay, so it's take more time than normal or traditional Naive Gaussian elimination method, because here we need to normalize usually the diagonal coefficients. We divide it over the diagonal. If I have A here, so I need to divide over A in the first row, A1. That means I want to normalize this row in this case, so I get here once. The same things after I do these steps and elimination also. So I need to normalize this coefficient that comes at the diagonal. So in this case, we need more steps. Okay, more steps, two normal steps, one normalization and the second step elimination. So we need normalization and elimination like this one. So after that, after we get diagonal or identity matrix, it is easy to find this one, because this one here, you can see X here will be appear in the first row, X1, while X2 is equal 0. So this will equal here a B bar, for example. So directly this X1 is equal B bar. And here, for example, this is X2. And here I have B2, for example, bar or prime here. So in this case, X2 is directly equal B2 and no need to do back substitute. Let's take this example. The first things, as we know, if we have equations, we construct augmented system or large system that we have. So this is the large system that we have, or the dynamic or the equation of the systems. We have here, this is the A matrix, and this is the unknowns, and this is the solution, B matrix. So after that, we build this, the large system. We put here the B's with the dynamics, the A's. So the first step, for example, if you want to solve the problem for X1, so we start, for example, for X1 and then X2 and then X3, depending on how many columns that we have. Okay, so the matrix must be square. So after that, what we do here, so the first step, as we said, we need to make this one, the coefficient. This is the diagonal coefficient. Okay, so we need to make this coefficient 1. So by divided over 1, A11, the entire row number 1, I will divide it over the buffed element here. Okay, so this will be A11, and this also divided over A11. That means the first step, I will normalize the buffed element for X1 in the first row. I will make this one, or I convert this to 1. As a result, so what you will get, this now become 1, and this I will have new variables like this one. And then I will use this row, this the buffed row. Okay, the buffed here we use Naive elimination. Okay, because we don't do any buffing. Okay, we don't do any partial buffing or scale buffing, so we directly assume the first row is the buffed. Okay, so that means we use Naive elimination. So here this is 1. After that, I will use this row as a buffed to convert this to 0. I will make this 0, and I will make this 0 below the diagonal. Second step, after I eliminate this one, we will have change in these coefficients. So next step, I need to go to eliminate X2. In X2, ya shabab, so here, if assume this is the buffed now for X2, we need to divide it over A22. That means I want to normalize now row number 2. So to make the diagonal coefficient equal 1. So I will divide the entire row over this coefficient. So in this case, this become 1. Then I will use this coefficient, becomes 1 now. After that, this will be 1. To eliminate this to become this 0, and this also, I need this to be 0. Let's complete the example that we have here, or the algorithm, the steps that we have here. So here in the steps of the Jordan, we need the number of steps. We call these passes. The number of passes is equal the number of equations. So within each step, we have to perform 2 steps. Normalization step. That means we normalize the diagonal element. That means to reduce the diagonal element to 1. If I have any coefficient, we need to reduce the diagonal element to 1. The second step, it is elimination step. After we make this 1, or convert the diagonal element to 1, we need here to reduce the off-diagonal element in the same column after we normalize the diagonal element to 0. The first step, we normalize the diagonal element to 1, and after that, we convert the off-diagonal element, that's the element that's not on the diagonal, to 0. Okay, so after that, we will get identity matrix. So here, for example, this is the steps of our load that we have. Here, this is the dynamic matrix, because here we use standard Gaussian elimination without any buffed. Okay, so we'll assume this row will be the buffed row. This means this is Naive elimination. Okay, this buffed row. So in this case, because this buffed row, and what's the diagonal element here? This is diagonal element. It is. So here we need to normalize the first row by dividing by the diagonal coefficient A11. I will divide it, row number 1 over A1. So in this case, I normalize this one. That means I make this one, because this will make the matrix at the end identity matrix. So after we do this one, so this we have changed here after we divided in this one. So we have changed in this coefficients. The first, so this will become 1, and the other change, for example, to have A12 prime, A13 prime, and B1 prime. Okay, this is the coefficient that we have. The second step, after we normalize this one, we need to use elimination now at x1. I need this coefficient, so I need to eliminate this one, these two below it, to make these zeros. So now the second step, eliminate x from the other rows. I try to eliminate x1 from the other rows. So this is 1, so I need to eliminate x1 here and x1 here. So we use Naive elimination. So the new row 2 is equal to old row 2 minus the coefficient here, multiply by, before we take ratio between the coefficient that we want to eliminate over the coefficient of the buffed, or over the buffed element. And now because the buffed element is already 1, so we have here A12 over 1. So no need to type this one. So we have only A21 multiply by row 1. So we use row 1 to eliminate this coefficient. And also, this is row 3, new row 3, it's equal to old row 3 minus this coefficient multiplied by row 1, and we subtract between them. So as a result of this step, we will get here, this is already diagonal, element is 1, and here I have 1s below it. So that means I cancel x1 now. Okay, so we might update the coefficient in our matrix. So next step, we want to work on x2. We will do the same things, but here in x2, we need to look for the diagonal element. We need to normalize the diagonal element. Okay, so what's the diagonal element? This is the diagonal element for x2. So if we look for this one now, here, if you want to normalize the second row by dividing by the diagonal element x a2 2 dash. So this coefficient. So I will divide it row number 2 over a22 dash. So in this case, I will normalize this one. So now the diagonal coefficient becomes 1, and I have change in this coefficient. And then I will use this coefficient to eliminate x2 or the off diagonal element. I need this one, so I need to cancel this coefficient from here and also to convert this one to 0. So we need elimination step now. The elimination for 2 for the other rows. That means I want to cancel this coefficient and this coefficient. So here row number 1 it's equal old row number 1 minus the coefficient here multiplied by row number 2 because I use this as a buffer now for the elimination, for the next step elimination. Row number 3 it's old row number 3 minus the coefficient that I want to eliminate multiplied by row number 2. This is the buffer row. So as a result we get 0 here and 1 already for normalization and 0 here. This is the next step. The third step, if you look here, we need also another diagonal coefficient, this one. This coefficient, we need to normalize it and then to remove or convert the other coefficients to 0. So the seventh step we can do, we need to normalize this one. That means I will divide row number 3 over A33 double prime. I will normalize this one, I will get here 1, this coefficient to be will change. After that, because in this one, now I want to do elimination by cancel this coefficient. That means I will cancel x3 from this, the coefficient of x3. This is the elimination for x3. From the all other rows, we can see here, for example, row number 1, it's equal all number 1 minus this coefficient multiplied by row number 3, because this is the buff that we use it for elimination. And row number 2, it's equal row number 2, the old one, minus this coefficient, this coefficient that we want to cancel multiplied by R3. So as a result, we get this matrix now. So this matrix now, we do normalization for the diagonal element and elimination for off diagonal coefficients. As a result, we get here identity matrix. So it is easy, we can type here x1 just equal b1 double prime and x2 it's equal b2 3 or triple prime. Okay, and here I have x3 is equal b3 triple prime. Okay, so no need for back substitute. Okay, so this will be the solution. The exact solution for this system, we have x1 equal b of 3 prime, x2 b2 triple prime, and here we have x3 b3 triple prime. So this is the solution and no need for doing back substitute. Any question, يا شباب؟ أنت Okay. All clear إن شاء الله. Okay, so let's take this example or look for this example just to show the steps. After that, you will have the last method in this topic to go to topic number 5. I will jump to topic number 5 and then I will return back to topic number 4. Okay, so here we can see we have here a matrix 3 by 3 or system 3 equations and use Gaussian-Jordan technique to solve the system. So at the beginning we build our last system, okay, from the coefficient of the unknowns and also the outputs. So here we have large system like this one. After that we do normalization for the first row we divided over the buffed element. We call this the diagonal or the buffed element. So you'll get this new row, number one. After that, we eliminate the terms x1 terms from the second row by subtracting 0.1, this one, from the first row, and subtracting 0.1 times first row from the second row. Okay, and we do the same for the third row. So after that, we get this one, and then we normalize the second row to get here once, and we do elimination for these coefficients for x2, and then we normalize x3 by dividing over 10.020, and after that we eliminate these two coefficients for x3, and then for example this will be the final step. We just equalize this one, x1 for example it's equal 3, and x2 it's equal minus 2.5, and x3 equal 7.00. Okay, and this is another examples. Inshallah, you can go through them. Inshallah, when I submit this one, the revised one. Any question for this method? I think you already know this method, but you want to. Yes.
Doctor.
Yes.
Here يعني هنا ما نقدر بعد نسوي تبديل بين الصفوف ونضرب مثلا كاختصار.
You mean to have to do swapping, interchange between the rows?
Yeah.
This method it's depend. If you want to apply here, if you look for this one, Gaussian Jordan, it's used to convert the matrix from A to identity matrix. After that, we get the solution without need for back substitute. هذا الidea. You can do it. What we have here in this example, we do Naive Gaussian elimination. صح? We use Naive Gaussian elimination. ما استخدم buffed. But if you need to improve, if you want to improve the accuracy, you can use partial buff. مثلا لو شفت هذا الكوفيشن is very very small here مثلا assume. خلينا نشوف أنا مثلا أنا أقول لك هنا يمكن تستخدم إني البافت here. لو this coefficient, let's return to this example. Assume this coefficient is 0. Okay, this coefficient is 0 here. This coefficient is 0. Okay, so here we cannot use this for 0 here because we need the diagonal to be once. I'm right?
Yeah.
Yes, here we can make buffed or interchange. We can have here because if you do elimination for this coefficient and you keep this 0 and this also others, so you might have this and you don't have any solution for x1, and this also will affect your solution. So as a result, if this is 0, we do interchange. Also, if we have here, for example, in your solution, one of the diagonal is 0, you might interchange. So if you change this one, for example, if this 0, if you change this one here, so this becomes 0. So also we need this to be 0. Okay, so or also if the value here is very very small, for example, this is power 10 minus, for example, 6, almost 0, and this is very very small with compared with the others. Sometimes we do buffed, otherwise partial buffed, or we do يعني scaled buffed. So at the beginning here we said that we can modify the steps. Here we use Gaussian elimination, Naive elimination, this example, but we can modify this one to do partial scaled buffed, or we use partial buffed, any method you can use, because the idea we do normalization, the rest is the same. Okay, and also we eliminate the coefficient above and below the diagonal. Okay. Okay, so any question you Shabab, usually if you have here 0, you might avoid it by interchange. If it is 0, for example, and you want to use Gaussian technology, you might do partial buffed and solve it. Any question?
Clear.
Did you study this before, يا شباب?
Yes, we did.
Yes.
Yes.
Okay. Okay, so the second type of methods, it's for trial diagonal system or banded systems. Okay, so here we will have some algorithms that use it to find a solution for trial diagonal and banded systems. So here, what's trial diagonal systems? That's the matrix that's contain 3 diagonals, and the rest are zeros. So these 3 diagonals and contain non-zero elements or non-zero terms that's contained in the mean diagonal. This is the red one, and we have here above of this one we have the super diagonal, and below this one we have the sub diagonal. So in this type of equations or this type of systems, we have some algorithms that help us to solve these type of equations. So usually, يا شباب, what we do here, we solve this in 2 steps or 3 steps. For example, if you want to solve it easy, sometimes some students they might, for example, make the sub or the mean diagonal once. Okay, like what we do in the Gaussian. They might, for example, make this once, and then, for example, eliminate the coefficient here below the diagonal at this coefficient, make these zeros. Okay, and for example, and after that, we solve the problem, because what we have here above the diagonal, this will not change, because this is we have zeros here and we have zeros at the bottom, so this coefficient will not change. And we use this coefficient to do the elimination. But here for numerical method, we have another method, algorithm. So we call this Thompson algorithm. So what's the Thompson algorithms? Here it is used to find the solution by doing algorithms. Okay, and no need, for example, to normalization or simplification. Okay, just we know the diagonal, the super diagonal, and the sub diagonal, and the mean diagonal. After that, we apply this algorithm to find the solution of this one. This is what's the benefit of this course. Trial diagonal, as we know, this is happen or exist in different application. It usually needs less storage because the most of the majority of the matrix are zeros. Selection of buffet rows is no need here for some condition. It's work, for example, official if you want, for example, to solve this by Gaussian elimination. Okay. So based on naive elimination, as we said, Gaussian elimination, we do forward elimination, back substitute elimination. But here, for example, in this one, the super diagonal will not affected if we do this elimination. And the elements in the mean row and B only will update. That means this one, the mean row, will update. Okay, and this one and the B's. So let's look for this one, the algorithm that we have. So this is the trial diagonal matrix that we have. Okay, we need, for example, to update the values of A and D's and B's. So by using this algorithm, we'll convert this matrix to a new matrix by converting the A's to zeros. Some they prefer to make this ones, do normalize. Or by using this algorithm, we don't need to normalize this one. It might be any values. Okay, so this will make A zeros, and what we have, C's will not change because this is here we have zeros and here we have zeros. There is no change, and here the D's will update and the B's will update. So I have here change in the D's, expect the first one. And also this is the B1. So these B's will update and the D's will update. So as we said here, this coefficient will not change because we multiply by zeros. Okay, this coefficient, because here we have zeros, we multiply by 0, and we use this buffed element, this buffed row, to do the elimination. This is our buffed row. We use it to do the elimination here and here, if we need. So this is algorithm for the trial diagonal systems. So in forward elimination, we have DI, the new DI, or the updated new. Let's type here in. It's equal to all minus ANI minus 1 over DI minus 1 multiplied by CI minus 1. That means we want to pick the values of C's here, and D's, and A's, and we put them in orders. Usually we put them in vector form. After that, we do this because we have updating only in this coefficient, in D's and B's. A new B's, what's the B's? B's will equal the old B's. A's at I, this will be I minus 1 over D minus 1 multiplied by previous B. And this algorithm applicable only from I equal or greater than 2 to n. So we start from I equal to. Okay, because 1, at 1 here we don't have any change. So this is the same. Okay, so we need to find row number 2. Okay, this will have change at D2. So D1 we don't have any change, so no need here. Okay, so in this case we start from 2 now. For this and for this, also B is the same. No change will happen to B. The same value. And back substituting, if you do back substitute here, this will be the last one. If we have, for example, matrix 4 by 4, the last coefficient will be x4. So you start from power n. Okay, because here it is easy. You can see this is xn. xn, it is easy equal b n prime over dn prime. So we start from this one. After that, back substitute. Okay, so xn equal bn prime over dn prime. So here we have this one. So I have bn over dn. I start from back substitute. And then we reduce by 1. We use this general form for the rest. Okay, so here we have n minus 1. For example, if it is 4 by 4, I have 4 minus 1, so I can compute, for example, x3. Okay, so here we can compute x3, and we do this one. 3, I put here x3 equal d3 over b 3 minus c3 multiplied by x4. And I know the value of x4. Okay, so here, for example, I compute here, for example, x4. This would equal b4 over d4. After that, I will do for x3, for example. x3 here, you can see it is equal, substitute instead of I by 3, so I have 1 over d3 multiply by b3 minus c3 multiply here by x plus 1. So I is 3, so I have x4. So this algorithm, by knowing the value of x4, I know c3, b3, and d3. From the matrix, I compute x3. I will do the same for x2. So x2, I have d2, b2, c2, x3. Okay, so here in this solution, we usually have algorithms more than traditional what we choose solutions that we have, mathematical solutions. So here we have an example here. Look for this example. We have this example. It is confused for you because all the parameters are the same. Okay, inshallah, you will provide another one. We have different coefficients. For example, C's are the same, B's are the same, and D's are the same. So you cannot recognize what coefficient we pick. Inshallah, I will change this one. Here we have, for example, you can see we build a vector for this, for example, this, the mean diagonal, for A's, the subdiagonal, and I have C's here, super diagonal, and this is the solution that we have. You can see this is, we have less coefficient in these two columns. After that, we use the elimination method. So this is the elimination algorithms. We have two algorithms here, and we have here the back substitute. Okay, so this is, we start from the maximum will be x4, and this we start from x3 because here x3 x3 2 to 1. So this is the solution that we have. So this is D's, A's, and C's and B's for forward elimination. Because D1 we have it, not change D1. D1 will be the same. Okay. D2, the new D or D2 is equal to all D2 will be 5 minus this coefficient. So I have new D2 will be 4.6 and B2 will be 6.6. I will go for D3 or the third term in the diagonal. So this will be the old one is 5 minus A2 over D2, and this would be 5.652, depending on how many significant figures we use it here, or decimal number. So we do the same for the rest, for example, until D4. This we call this forward elimination. From the forward elimination, we get this new matrix or new vectors. Okay, because we said C's will not change. Okay, so we have change only in A's. A's will become 0, and this will be the new D's, and this is the B's, the updated, and C's is the same. So after that, by doing a back substitute, I will start from xn, and xn here is equal x4. I will compute this one, and then by doing this algorithm, so it is from I3, it is n minus 1. So I have 4 minus 1, 3, n minus 2, n minus 3. Okay, until we get 1. This is the last term. Okay, so we substitute this one by algorithm. We can develop our codes to find the solution of this one. Okay, this is the end of this example, and this is one code using C. The C code for this method. Okay, any question here, Yashaba?
Doctor, from where get C and B?
Which one?
C. C3, C2.
C2? Yes, this C's. Yes, this C's.
From columns here.
Yes, this you can see المين diagonal. هذا المين diagonal this. هذا this. ال5 is all 5 are the mean diagonal. Twos, these two these are the C's in our algorithm. Okay, and this coefficient are the A's, subdiagonal. So at the in this elimination, this will convert this to zeros. So here we'll have zeros later, but our algorithm will not show the steps of this one. Just we do this one, we try to update the matrix, because what we have, as we know here, by doing the elimination, Gaussian elimination here. Okay, if I use Gaussian elimination, any Gaussian elimination, I use it here, apply it here. So what I will have this one, upper triangle matrix, because this upper triangle, because I have here below the diagonal, the mean diagonal are zeros. Okay, and here C's will not have any change, because the C's will not change because we multiply by zeros. Coefficient here are zeros, so when I multiply and subtract, this will not change the coefficient here. So what I will have, I have only change in this coefficient. D's from D number 2 to Dn, and B's from B number 2 to Bn. A's will go 0, and the rest 0 will not change. So these zeros here will become zeros. We don't have any change in this coefficient. And also here I have zeros. So what we need, I use these columns to update the matrix. So that means I want to compute this new vector. Cs will not change because I don't need to do any updating. I have here change in Bs. So this will save our time in the logarithm in our update, because no need to do any updating for the Cs. So you can see we update only by doing the elimination. We updated these and Bs. After we do this updating, we will get this new matrix. This the new matrix, the updated matrix. And then after we update in the matrix, we do back substitute to find the value of the unknowns. Any question here, Shiva? Any question? Okay, so if no question, I will go to unit number 5. And unit number 5 is talks about the curve fitting. Okay, or recursive least square regression. Okay, and usually يا شباب, as we know, this is from chapter يا شباب 17 point chapter 17 sections 1, 2 and 3. Okay, so here usually, as we know يا شباب, usually we have a data. Okay, and data, this for example consists of spirit data x's with respect to y's. And this data, it's for y, but for function for some independent variables, for example x, but underlines relationship between them, it's unknown. Okay, and usually this data, it might be measured data or tablet data. So here we want to find or determine the function, or we can say the curve that describe or describe the relation between the x's and y's. Okay, so we call this the best fit. So the approximation for these unknowns, f of x, we call this curve fitting. So curve fitting, it is just or least square regression. In general, are technology or techniques that use it to draw or to shape the data in form we approximate all the variable or real data that we have. So usually we have a different type of estimations or a method that's use the curve fitting. For example, least square regression and also interpolation. So a least square regression, usually it is it's contain noisy data or disturbance. Okay, and this usually and if affect our results. Interpolation, usually the data points are known. Usually the data points are known exactly, and we don't have any noise. And usually interpolation, it's used to protect the value, for example, at x at discrete points. Okay, not if you want, for example, to estimate or protect values at x, for example, or any discrete point between the points that we have it in the table. So during this topic يا شباب, inshallah we'll try to cover the best fit of the line by using least square regression and also interpolation methods, polynomial and also linear type. So what's the curve fitting? So the curve fitting is a sample fitting analytical solution of the equation to a set of measured data. If we have any measured data like this one, so this is the points or the data that we have. These points represent the data. So here we want to draw or have a curve that's, for example, approximate or how represent the given data in a best fit. So, for example, we have this data. We need here to determine the values of the coefficients A and B and C and D that will best fit the function that we have. Best fit the data and best approximate of the function that we have. So why fit data to the curve? Usually we want to observe or quantify the general trends. If the trends of the data, for example, we have here a linear trend or nonlinear trend, for example. Also, we need this curve fitting to remove the noise from the function, because we use this estimation, the measurement, and the model that we develop to remove the noise and error. Fit measured data to analytical equation to Excel. Meaningful parameters. Estimate data between discrete points, or predict data between discrete points by using interpolation. Find the maximum or the minimum. And also here, derive a finite difference approximation. Here, for example, we have here a data. We can see this is the point that we have. We have two methods of approximation here, or for a curve fitting. As we said, one of them will be the linear regression, and the linear regression usually we draw a line that's not connect all the data. This line, it minimizes the error. Okay, and you can see this is linear line, but not goes cross or not connect all the data that we have. And here we have interpolation here. Interpolation here, it might be linear or curvely linear. So in this case, the function or the graph that we plot should connect all the points that we have. So both techniques use graphs to describe or to fit the curve all the points between the discrete points and the intermediate estimation. If we have also, if I have this point, what will be the function if a new point appears here? So we have protection of the points between at a discrete points. Least squares regression does not connect the points. Okay, but here we look for upward trend of the data within the straight line. And while interpolation here, linear, we use a straight line segment that's connect the dots. So here, we have the least square or the best fit, and this we have linear interpolation. You can see we have a line that goes through the points, all the points there. And this usually the very common in engineering. We need to do something like this one to approximate this one. But sometimes the data we have a paired or randomly location of the data. So in this case, it's not easy to use a linear type, and the linear type usually on the linear approximation will cause different errors. So as a result, we might use curve linear interpolation or polynomial type. Okay, so use here curve to try to capture the suggested data instead of line interpolation. So our goal in this chapter to develop a systemic and objective methods to drive such curves. So we'll give you a table of data. After that, we'll use this data to find the best fit and also to drive the curve of these data. That means we want to approximate the function by itself. So at the beginning of this chapter, we will start with linear regression, and after that, we'll cover the linear regression, and then we'll talk about the nonlinear regression and how we can linearize these types. If we have, for example, the relation between the input. Usually here we have a linear relation because this the title here is linear. So here we might use the line equation to represent the linear equation between this is the y, it's equal, for example, a0. Let's type it. So this is y equal a0, for example, plus a1 multiplied by x. Okay, so this is the line equation that we have. So here we might use linear equation to describe the relation between the coefficient that we have and also, or the data that we have, the x's, the unknowns, and the function and the outputs. But because usually this data it's affected by disturbance or by noise, so we need to have another term, we call this the error. Error here in our measurement. So usually we have an error in our measurement. So if we rearrange this equation, you can see this is the error. It's equal the measured output minus the model that we developed. Okay, so the error here, it's equal our measurement, Ly, okay, minus the model or regression model that we developed. So the regression model is nothing, just a0 plus a1 multiplied by x. So this linear regression, it's used to minimize the difference between the data and the curve plotted. And we can see this is the sampled example of this one. We use this for linear relation. So this is the mathematical explanation expressed here. While here A0 and A1 are the coefficient that we want to compute. Here, for example, A1 it's represent intercept, A1 represent the slope, and E represent the error. Okay, between the model, this is the model, and this is observation or our measurement. So during this topic, we will study how we use the data to find the model or to develop the model and to find the coefficient of this equation. And then, for example, how we measure, for example, how good this fitting, what we did, the goodness of our approximation or our modeling. And later, after this one, we'll go to nonlinear types when we have the function, the relation between the input and output, for example, exponential, or we have saturation, or we have sine, or we have cosine like this. Okay. Okay, so this linear regression, for example, if we have here a point of data, we usually draw a line that's not exactly connect all the data that we have. Okay, so we draw a line. After that, we measure the error between this measurement and the line or the best fit that we introduced here. Criteria for the fitting, we have different criteria for doing this fitting. One of them by minimize the sum of the errors, or minimize the sum of absolute value of the errors, or for example minimize the maximum error of any individual points. Okay, so this is the error. As we said, the error is the difference between the model or the observation and our observation or measurement minus the model that we have or subtract from the model. So we have three criteria to minimize this one. Either by take this one, minimize the sum of the errors, minimize the sum of the absolute value, minimize the maximum error. So if you look for this one, this is a classification that we talk about here. For example, when we talk the sum of the errors, we take only the sum of the errors between them. So this does not work because the negative value and the positive value can cancel each other and misleading to the overall criteria, and we cannot recognize this error. So for example, if this we have here data and this is our best fit, and we have here this point, for example, 1 and point 2. located at the same distance. The distance from here to here is the same, and this is the same distance from the best fit, and these 2 points of error or noise, this one and 2. So this positive value and the negative value will cancel each other, and the effect of these will not appear, because here we take only sum of errors. Here the sum of the magnitude of the errors. Also, if we take only the absolute value of the error, this does not work because it does not lead to a unique solution. Okay, if you do, we do not find a unique solution. The third criteria, by computing the sum of the squares of the errors. This type will work because this lead to a unique solution. Okay, so this is so for example, if we have here any straight line based through the midpoint in the connected line, expect the perfectly vertical line. The result is we'll minimize the equation. That means if we minimize the equation, we might find the best fit here. So this will cause an error. As we said, this will cause an error because we have here a point located here, and we have also a point located here, for example. And this point, if it is located at the same distance, in this case, the effect of each will cancel. The second criteria, any straight line fills within dash lines. If we have this dash line, will minimize the sum of the absolute values. So any values, any straight line within this dash will minimize the sum of the absolute value. As a result, we do not have a unique solution or a best solution here. So we look for something that's we provide us a unique solution. Okay, because the effect of the sign here of the error will eliminate it. But the solution still not a unique fit. Okay, and the previous one also we have the problem, and this figure we have the problem with positive and negative errors that can cancel each other. So the third one we might use with the square type. Okay, square type. Square type, or the square type that we have it here, we use it for the best fit. This will work and provide us the better or the unique solution for our solution. So the better fitting criteria that we might use is here by using the sum of the square of the errors or residuals. Okay, this type will provide a unique best fit for the given data of or the given set of data. Okay, and the sum of the squares of the errors is a function of 2 fitting parameters. You will see this one. So this is a sum. The errors here, or the sum of the square of the errors, is a function of 2 fitting parameters. A0 in our equation, this plus A1 multiplied by x. So that means here, by minimizing this error, so what we need to find this coefficient A1 and A0 and A1. So one way to do this one, by minimizing this coefficient with respect to this, with minimizing the error with respect to this coefficient, because we try to minimize the error. Our objective to minimize the error between the measurement that we measure by device and also our model that we develop. So this is the least square criteria that provide the best fit. And SR is the sum of the squares of the residue between the data points and the regression line, or this is the estimation that we have. So to have the best fit, as we said, we need to minimize the error with respect to the parameter that we need. That we need by use partial derivative with respect to 0. So we take partial derivative here for the error with respect to A0 and equalize this to 0. And we take partial derivative for the error with respect to A1 and equalize this to 0. And after that, we rearrange this equation like this one. Okay, and do we know the coefficient of this one, the sum of this constant, so we give us in A0. So after we derive this one and do rearrangement here by equalize the equation, we finalize with this final form or final equations. Okay, so by breaking up the sum here, for example, we finish with this one. So by solve this one by any Gaussian elimination, we might find this solution. A0 and A1, we start usually in the solution by computing A1 because A2 is dependent on the value of A1. A1, we find it by this one. So the number of terms that we have, the number of data multiplied by the sum of xi's multiplied by yi's. And this minus sum of xi's multiplied by sum of y's over n, the sum of x squared minus the sum of x all square. Okay, and A0 just y, mean of y, minus A1 multiplied by mean of x. That mean in our table here, for example, if we have a table, I have x data and I have y. So to find A's, I need this coefficient. I need to have a column here, x multiplied by y. After that, I will take a sum at the end. This will be sum. Here also, I need a sum for x. This I will find it here. And multiply by sum of y. This I will find it here. Here also, I need x squared. I will take x squared here. After that, I will take a sum of x squared. Okay. This is x sum of x squared. So this is the value I will square it here. And n is the number of the data that we have. How many data that we have. And also for columns, for example, column x, I can compute the mean, and also I can compute the mean for the y's. So after that, I solve these coefficients. If I find these coefficients, I will find the best fit line, or the line that represent the best fit. Okay, so the equation that we have it here, it's with two unknowns. I have the unknowns is A0 and A1. Okay, so it is easier to find this one, or the solution after we normalize the equation. Okay, so we might use these rows to find this. Any question until here? Later, Shabab, after we do this modeling by find these parameters, we will study the goodness of our fit. That means we want to know how well does the function fit the data. Okay, is the fit is a linear is the best fit or no? Or we can use, for example, quadratic or high order polynomial, or for example, linear function. So we went here to know after this one how we went, for example, to quantify the goodness of our fit by measuring the error, standard deviation, and standard error of estimation. Okay. Yes, this is just a graph that represent small versus large regression errors. Here, for example, we have small errors between this represent the best fit, and here we have large fit. So we need to study how good this fit, or the goodness of our fit. Here, ya shabab, so this is just to find the errors. Here, for example, if we have data, this is the data, for example, for x's, that's all. And this is, we have the values for y's. Okay, so here we compute the difference between y's and the mean of the y's. And here, this is the least square error. Okay, and this we have here a model and the measurement and the model that we have. And this, the last thing at the column, this is represent the sum of the data. Let's look for this example. This example is the same thing as what we have before. Usually we give you this one, x's and y's, and you need to complete the table to find the model. As we know, as we said beginning, the formula, let's pick the formula here, the form here, this one. This usually will be the given this one. Okay, can you see this one?
Yes.
Yes, okay. Okay, you can see here how many points we have. We have 7 points, so n is equal 7. So here to find A1, to find the model, we need n is equal 7. And after that, I have the first column will be xi multiplied by y. Okay, so here I have column x multiplied by y. So after that, I will take a sum of them. If you multiply x by 1, so I have 0.5. Here I have, for example, 5, 6, 16, like this one. You have here multiplication, and then you will take sum at the end. So we need this at the first term, multiply by n. And the second term, I take sum for x's here, these points, multiply by the sum of y's. The sum here 24, so multiply by sum of x's. And here what we have, sum of x's is 28. Okay, and after that, this the two coefficient, I will take x square, x square, I will take this square, like this one. After that, I will take a sum at the end. And this also x square that I have it here, this x, I will take it all square. Also, I want to compute the mean for the x's. So 24 over 7 points, so this will be 4. I have also the mean of the y's. I have 24 over 7, this will be 3.28571. It depends on how many significant figures that we have, or decimal that we have in the solution. So from this one, from this information, I can compute LA1 and then I compute LA2, LA0, sorry. So the best fit using this least square will give us this solution. So LA is intercept point and LA1 is the slope. Any question here? So after that, we went to measure the errors, okay, the standard deviation and the standard error of estimation. Okay, so here, for example, this is the error that we compute is the sum of the squares of the errors between the data of regression, and ST is the total sum of the squares of the errors between the data and the mean. Okay, so we'll have more discussion about this, inshallah, in the next class. Okay, so also, inshallah, next class, inshallah, we'll try to talk about coloration coefficients. That's it's used to give us a measure of the errors of our, for example, fitting. How this fitting is perfect. Okay, so here, if you look for this one, the coloration coefficients, it's equal the difference between ST minus SR over ST. Okay, while ST is classified at the spirit of the data about the mean. Okay, how the data is spirited about the mean, and RS is quantifies, disperse the data around the best fit. Okay, if the model that we developed is a copy from the measurement, so in this case the error will be 0. Okay, if the error here of our estimation, if the model that we developed is a copy from the measurement, the exact solution, so in this case the error here will be 0. So in this case this will be 0, and I have here ST over ST. So in this case the coefficient R square is equal 1. Okay, that means the model that we developed explains 100% of the data that we have. If we have reduction, so we can determine how improved that we have in our fit. Okay, so it might be 86 or 50 or no improvement, for example, if R square equals 0. Any question, Ishwar, until here?